Hello everyone, welcome back to our physics class. And for today, we will discuss about module 4 and 5 with the concepts of electric potential energy and potential difference. At the end of this episode, you will be able to relate the electric potential with work, potential energy, and electric field. Calculate the electric field in the region given a mathematical function describing its potential in a region of space, and solve problems involving electric potential energy and electric potentials. But before that, let us recall the concept about work. Work is done when a force moves something in the direction of the force. An object has potential energy by virtue of its location. For example, doing work by lifting an object increases its gravitational potential energy. Therefore, we can say that work is defined as the product of displacement and a parallel applied force. Or, we can write that in equation form, work is equal to force times distance or displacement, or work is equal to force multiplied by the cosine theta multiplied by the displacement. If the unit of force is in Newton and displacement is in meter, therefore, the unit of work is in Newton meter or joule. Let us also recall that potential energy is defined as the ability to do work by virtue of position or condition given the equation U is equal to mgh. While kinetic energy is defined as the ability to do work by virtue of motion given the equation K is equal to 1/2 mv squared. The work energy theorem tells us that the work done is equal to the change in kinetic energy. If work is equal to force times distance, we substitute the equation for force, which is mass times acceleration, and the displacement. Simplifying the equation, it will give us work is equal to 1/2 mv final squared minus 1/2 mv initial squared. Or we can simply say that work is equal to the final kinetic energy minus the initial kinetic energy. Or we say that work is equal to the change in kinetic energy. Last time, we introduced the idea of electric field to understand how one set of charges and the sources of charges exerts electric forces on other charges. Now, to understand the electric energy, we will introduce the concept of electric potential. Similar to any object, charges moves from one place to another. A charged object can have potential energy by virtue of its location in an electric field as shown in the illustration. Work is required to push a charged particle against the electric field of a charged body. An external force F moves the positive charge from point A to point B against the electric field force QE. If work is equivalent to force times distance, we substitute the equation of force, which is equal to electric field multiplied by the charge. Therefore, at point B, we can say that electric potential energy U is equal to electric field multiplied by the charge multiplied by the displacement. The electric field does negative work, while the external force does positive work. In the illustration, you see lines from positive to negative plates. You also see lines that is perpendicular to these lines. Which do you think represents electric field? And what does the other lines represent? The lines from positive to negative plates is called electric field, while the lines perpendicular to the electric field is called equipotential lines. An equipotential line or surface is all at the same potential and is perpendicular to the electric field at all points. The electric potential V at any point in space is defined as the potential energy per unit charge. Or, we can write in equation form, V is equal to PE over Q. If the potential energy has a unit joule and charge has a unit coulomb, therefore, the unit for electric potential is in joule per coulomb. The electric potential difference between any 2 points is defined as the work done per 1 coulomb of charge between 2 points. Or, we can write that as V is equal to the work done per unit charge. Potential difference is measured in volts and sometimes referred to as voltage. Work is done by the electric force to move a charge from point B to point A. Therefore, we can say that the electric potential difference is equal to the potential at point B minus the potential at point A. Or, we can simply write that as the electric potential BA is equal to the work done BA all over Q. Since work is equal to a change in potential energy, therefore, the change in potential energy is equal to the potential energy at point B minus potential energy at point A. Or, we can simply write that as delta PE is equal to charge multiplied by the electric potential difference. The unit 1 volt is also equal to 1 joule per coulomb. Take note, when the test charge is moved in the field by some external agent, the work done by the field on the charge is equal to the negative of the work done by the external agent causing the displacement. Therefore, we can say that the work done is equal to negative change in potential energy. The effect of any charge distribution can be described in terms of electric field or in terms of electric potential. For a uniform electric field, the potential difference is the product of the electric field and the distance between 2 points. Or, we can simply write in equation, V is equal to the electric field multiplied by distance. Since work is equal to charge multiplied by the electric potential, we say that work is also equal to force times distance, and the electric force is equal to the electric field strength multiplied by the charge. Then we substitute the equation for force, wherein force is equal to electric field multiplied by the charge multiplied by the distance is equal to charge multiplied by electric potential. From the equation, we cancel Q or the charge. Therefore, we have electric potential is equal to the electric field multiplied by distance. Rearranging the equation, we can say that electric field is equal to the electric potential all over distance. Another unit for electric field is volt per meter. Therefore, we can say that 1 Newton per coulomb is equal to 1 Joule per coulomb, which is also equal to 1 volt per meter. An electron volt is used as a unit in dealing energies of electrons, atoms, or molecules. 1 electron volt is defined as the energy acquired by a particle carrying a charge equal to that on the electron as a result moving through a potential difference of 1 V. Since potential energy is equal to charge multiplied by the potential difference, therefore we can say that the energy of 1 electron is equal to 1.6 times 10 raised to negative 19 coulomb multiplied by 1 volt or 1 joule per coulomb. We cancel the unit coulomb. Therefore, we can say that the energy acquired by 1 electron is equal to 1.6 times 10 raised to negative 19 joule, and that is also equivalent to 1 electron volt. Electric dipole is the distance between two equal point charges of opposite signs. Let's apply the concept of electric potential and potential difference in solving this problem. As a charge moves 39.0 cm in the direction of a uniform electric field, its potential energy changes by negative 1.86 times 10 raised to negative 3 joule. The magnitude of the electric field is 177 Newton per coulomb. Find the potential difference between the starting position and final position of the charge. What is the charge on the moving particle? Given the electric potential energy equal to negative 1.86 times 10 raised to negative 3 joule, distance of 0.390 meters, an electric field which is equal to 177 Newton per coulomb, we find the potential difference from the starting position to the final position and the amount of charge. If the potential difference is equal to the magnitude of electric field and the displacement, therefore we can say that the potential difference is equal to the negative electric field multiplied by displacement. Electric field does negative work. We substitute the values for electric field and the displacement. Therefore, we have the value for potential difference is equal to negative 69.0 volts. Using the equation for the change in electric potential energy, which is equal to negative QED, we arrange the equation to derive for Q. Charge Q is then equal to negative electric potential energy all over electric field multiplied by the displacement. Substitute all the values. Therefore, the value for charge is equal to 2.69 times 10 raised to negative 5 coulomb. That ends our lesson for today. I hope you learned a lot. See you again next time and have a great day.